All right, so in this video, I'm going to do a practice worksheet 6. So this is basically all the questions from worksheet 6 with some different values and some different examples, hopefully to give you a good idea how you can solve them. So let's just look at these equations that I gave you. First, one of our definitions of the net force is just the sum of all the forces in a given dimension, including direction. So you just add up all the forces that are in maybe the x dimension, and then you do it separately for all the forces in the y dimension. Another way of writing net force is just the mass times acceleration. This is Newton's second law, right here. We know that weight is just the mass times 10. That's a really simple yet really important thing to remember when doing these examples, that you can take a mass and you can get the weight or the force of gravity just by multiplying it by 10. And then some little trig reminders here. Our opposite is always going to be with the sine, and our adjacent side is always going to be with the cosine. So let's take an easy example to start. A frictionless pulley system has 3 hanging masses as shown. Calculate the expected acceleration of the system. It's really hard to see here, but each one of these is 50 kilograms. 50 kilograms, 50 kilograms, 50 kilograms. So right off the bat, I can say the total mass equals 50, 50, 50, 50, 200 kilograms. Now our next question, if we were looking for the acceleration, we're going to be looking at, we want to know the net force on this system, and that's going to equal the mass times the acceleration. So we already have the mass. We're looking for the acceleration, so we don't need to find that. We just need to find the net force of this system. Well, this is our positive direction. If it's spinning down this way, it's positive. So we need to think, how much weight is this 150 kilograms going to apply in this direction? Well, if it's 150 kilograms, its weight, or Fg, will equal 1,500 newtons. Right? If we do the same thing over here, this 50 kilograms, Fg over here is going to equal 500 newtons. Well, then we ask ourselves, what is the excess or the net force on the system? We have 1,500 pulling it in the positive and 500 pulling it in the negative. Well, we can see that our net force here, our net force, is just going to be, if we want to write it out, is 1,500 newtons minus, because this is in the negative direction, minus 500 newtons, which gives us positive 1,000 newtons. Okay, so now we have our positive 1,000 newtons, our net force, our total mass, and we can use this to find our acceleration. So 1,000 newtons in the positive direction equals 200 kilograms times the unknown acceleration. Well, if we just divide by 200, 1,000 divided by 200, our acceleration is going to be positive 5 meters per second squared. It's going to be in the positive direction because that's where our net force is directed. All right, let's move on to number 2. Number 2 is a little more of a challenge. Some of you may have seen this one in class already. We're going to do an example here. Okay, a 40 kilogram block accelerates down an incline with friction at a rate of 1 meter per second squared. Calculate the normal force and the friction force. Okay, so we want to know, what does the normal force equal? And what does the frictional force equal? Those are our 2 unknowns. Oh, a little off the page there. Okay, so this is a pretty big problem, and we have to take it step by step. The first thing that we're going to want to do is draw a force diagram and create a coordinate system. So if we draw a force diagram, let's make this dot our block. We know that one of the forces that will be acting on it is definitely the weight. So we'll go down, we'll say Fg. And then we also know that there's going to be a normal force applied by this surface to the block pointed perpendicular to the block. So perpendicular meaning directly this way, be our normal force. And then finally we have a frictional force, because look, it says an incline with friction. And friction always points parallel along the surface and resists the motion. We would expect this block to fall down this way. The frictional force is going to hold it up. So there's our force of friction. Okay, we don't know the normal force or the force of friction. That's what we're being asked to solve. The first step that I would do is to make sure you have a really clear understanding of your coordinate system. So you're going to want to draw your coordinate system. And since we are on an incline, we're going to draw our coordinate system at an incline. So match that coordinate system with the incline shown here. Now remember, using a little bit of geometry, we know that this 30-degree angle here becomes this 30-degree angle here. All right, so now the really interesting thing is that important thing is that because we've chosen our coordinate system to be along the surface of the incline, when we look at this acceleration actually becomes entirely an acceleration in the x direction, right? That acceleration will be going down the x direction. We won't have to deal with anything in the y dimension, which is going to be really helpful when we get to the end of this problem. Okay, so right now our only problem is that our FG is not pointed along any of the axes, so we're going to have to split that into its two components. We know that this component here will be FGY, and we know that this component here will be FGX. All right, now let's put some numbers in here. Can we give any of these numbers? Absolutely. Our force of gravity, well, we know that the block was 40 kilograms, so we know that the force of gravity is just going to be 400 newtons, 40 times 10. So now we need to think about, if we know this, our hypotenuse of our right triangle, let's see if we can figure out the values of FGY and FGX. Well, we know that FGY is the adjacent side of this 30-degree angle, so it's going to be the hypotenuse of 400 newtons times the cosine of 30 degrees. And the same thing here, except this side is our opposite, so we're going to use the sine of 30 degrees. Okay, and if I put those in my calculator here, let's see, we'll do 400 times the cosine of 30. That's going to give me 346 newtons. We'll round it off there. And then 400 times the sine of 30 gives me exactly 200 newtons in that direction. Great. Okay, so we've got some values. Got some values put on there. Now we can actually go ahead and answer one of our first questions. We've got it all balanced out. Sorry, not all balanced out. We have all of our forces along an x and y axis. It's not a balanced example because we have acceleration. Although the acceleration is only in the x direction. This is why it's important that we made our coordinate system like we did. Because there's no acceleration in the y, right? We can agree that this block is not accelerating through this surface or accelerating up into the air. So there's no acceleration in the y, which means that there must be balanced forces in the y. And so we can go ahead and say, well, this FGY is in the y and this FN is in the y. Those are the only two forces in the y. If we made a summation, if we made a net force of all the forces in the y, we would say it's a positive Fn and it's a negative FGY, which is just that 346 newtons. FGY. Now, those are the only two. We also know that if we made another FGY, which equals MAY, well, there's no acceleration in the y direction. So this is just 0. So this whole equation becomes 0, which means that we can set these equal to each other. So Fn minus FGY equals 0. And if we put in 346 for FGY, we get that Fn minus 346 newtons equals 0. We move it to the other side, and we get that Fn equals 346 newtons. Now that was a really long way of just saying that these two forces are equal and opposite. Equal and opposite. So this 346 is this 346 newtons. So you don't have to show all this work, but that's where it comes from. And that's how we use our two equations in the y direction. No acceleration, so this force must equal that force. All right, not so the case in the x direction, because remember we have this acceleration in the x direction. So let's go ahead and make our two equations for the x direction. All right, so we need to add up all the forces in the x for our first equation. Well, let's go ahead. I didn't say this clear in the beginning. We can do this. Let's call down the slope positive and up the slope negative. You're allowed to do that because coordinate systems are arbitrary. That'll just help us by putting our acceleration in the positive direction. Keep it simple. So we have, that means that this FGX is then in the positive direction. So positive FGX, or you could just write the 200 in there. I'm going to keep it just as a variable. Minus FF. We don't know that one yet. And the second equation is always the mass times the acceleration in the x, because we're doing the forces in the x. They both equal the same thing, so we can set them equal to each other. FGX minus FF equals MAX. And now we're going to plug in our known values for those forces in the x. In the FGX, we know that that is equal to 200 newtons. Not only 200 newtons, but a positive 200 newtons. Minus that force of friction that we don't know. Do we know the mass? Absolutely, 40 kilograms. Do we know the acceleration? Yep, gave it in the problem, 0.8 meters per second squared. All right, now we just need to simplify. So I'll bring my calculator over here. So 40 times 0.8 gives us a 32. That's going to become a newton over there. Let's keep everything the same over here. All right, and then we need to get this FF by itself. So we'll minus 200, minus 200. So you have 32 minus 200. It's going to give you a negative 168. The negatives cancel out. And this actually just gives you the magnitude of that force. When we go back to our diagram, we see that it's pointed in the negative direction. So this will just give you the magnitude. So when you go to write your answer here, it's best to put a negative just to show that it's pointed in the negative direction. Negative 168 newtons is your force of friction. And we got our normal force right here. I'll just copy it down here. 346 newtons for your normal force. So that's a pretty big problem. But if you go back and check, we made a force diagram. We split up this into its components. We recognize there's no acceleration in the y, set those equal to each other. We said there is acceleration in the x, so we need to use our two equations. We set them equal to each other. We plugged in our known values, and we solved for the unknown. All right, let's go try one off the back. A man pulls on a 40-kilogram box with a 250 Newton force that moves across the surface with friction and accelerates in the positive direction at a rate of 3 meters per second squared. All right, so let's go ahead and put all this stuff. This is 40 kilograms. This pull is 250 newtons. And there's an acceleration equal to 3 meters per second squared. All right, now there's two questions. What's the size of the normal force? And calculate the force of friction. So the same two questions from right before. All right, so let's go ahead and draw our force diagram as we start. I'm going to draw the force diagram down here so we can save that space for calculating. Here's our force diagram. Right off the bat, we got Fg, and we can go ahead and put a value for that. 400 newtons. 40 kilogram box, 400 newtons. Fn, up, I'm going to wait to put a value on that because it turns out it's not as simple as it looks in this example. Fn's up, we have the force pull here, 250 newtons at a 20-degree angle. I'll put that in a second. And we know that there's a force of friction resisting that pull. Okay, let's go ahead and draw our coordinate system in here. We're going to keep it right along the surface here. There's our x. Here's our y. And this is a 20-degree angle. All right. So to find the normal force, we first need to think about, well, one of these forces does not line up on an x or y axis, so we need to split it into its two components. And that is the pull from the man. So we have this would be F pull in the x, FPX, and this would be FPY. I'm going to go ahead and fly through this now. Let me zoom in on this here. It's getting a little small. Sorry if it's a little blurry. FPY is going to be the hypotenuse, 250 times, it's the opposite to that angle, so that's sine of 20. X is the adjacent, so it'll be 250 times the cosine of 20. If we go ahead and use our calculator here, 250 times sine of 20 gives me 85.5. And if we do 250 times cosine of 20, we get 200, and we'll say 235. 235 newtons. Great. All right, now we've got a more accurate force diagram with these now directed right along the y and right along the x. So to find this normal force, we now need to consider all of the forces that are acting in the y dimension. So let's sum up all the forces in the y. Let's make our two equations, actually. Well, before we do that, actually, is there any acceleration in the y? The answer is no. All the acceleration is in the x. It's all accelerating forward as the man pulls. So there's no acceleration actually in this y direction. So we know that all the forces will be balanced. So the second equation of Newton's second law is going to equal 0. But we need to think about, in past examples, we were just able to say, well, if there's no acceleration, then Fg must equal Fn. But if you think about it, we actually have another force in the y, this Fpy, that causes something to happen. So let's sum them all up. Let's say we have a positive Fn plus a positive 85.5 newtons from that Fpy minus Fg. I'm just going to say the 400 newtons from Fg. I'll put these little notes up here. That's Fg, that's Fpy. And that must equal 0 because that's what this equation equals. And we set them equal to each other. So now we have one unknown in an equation that we can solve for. So we have 85 minus 400 equals 0 when we add the normal force. So Let's add 400 to the other side, and let's subtract 85.5 from the other side. And we're going to see that the normal force equals positive 400 minus 85.5. 314.5 newtons. And it's a positive. So what does that show us in the example? That the normal force is actually smaller than the force of gravity because you have this support from the guy pulling it up a little bit. So the normal force doesn't have to be that full 400. It actually only has to be 314.5. So it gets a little less due to that support from that FPY. Okay, and now we're on to calculating our force of friction. Well, we need to sum up our forces in the X, our two equations. Let's add them all together. We have the force of friction. Well, let's do the FPX first. FPX, right? The pull in the X dimension is just this FPX, and we're going to replace it with 235 in a second. So that's positive minus whatever this force of friction is. And that's going to equal MAX, mass times the acceleration in the X. Two equations equal the same thing. We can set them equal to each other. Positive FPX minus FF equals the mass times the acceleration in the X. Then we'll see, as we always do when we get to this point, we have all the pieces to solve this equation for the unknown. Our unknown is what is the force of friction. So we only need to figure out what this is. Do we have FPX? Yep, positive 235 newtons minus, just keep that a variable since we don't know it. The mass is a 40 kilogram box. The acceleration was given to us, positive 3 meters per second squared. And look at that, we can solve for this unknown. Let's go ahead and do it. 40 times 3 is going to be 120 newtons. Positive 235 newtons minus F of F. We're going to subtract 235 from both sides. So we get 120 minus 235. So F equals, the minus signs cancel out. Remember, this is just going to tell us the magnitude. 115 newtons. 115 newtons. And remember, it is pointing in the negative direction, so we can't put a negative sign on there. If you have it over here, you don't need to put the negative sign because you have the arrow to show that it's going in the negative. So you have 115 newtons of resistance that's pulling that box in the opposite direction of that pull the man is applying. Same system that we used to find the force of friction in the last example. Okay, and finally our last example here. A 50 kilogram box rests on a surface with friction, connected to a string with 20 kilograms of mass hanging over the pulley. If the block and the surface create a 150 Newton frictional force that resists the motion of the block, ... what will be the resulting acceleration of the system? All right, so we have this block connected to a string that's got these two hanging masses here, and there's a little bit of friction between the surface and the block. Let's go ahead and figure out some things we know before we go ahead and make a force diagram for this one. So we have 50 kilogram box. Great. We have a frictional force. Let's just put that on there. Equals 150 newtons between there. And we know that that's going to point, I shouldn't put the arrow there, it's going to point backwards at 150 newtons on that block. This is 20 kilograms. There's two 10 kilogram masses. And that's about all the information that we're given. So there's a couple steps we need to take. We're really going to be looking at how this block moves, because that's going to be the one that's being resisted by the friction. So If we draw a force diagram for that box, we know that there's Fg equals 500 newtons. And there's a normal force, which actually, in this case, there's nothing else acting in here, so that equals 500. And we're just going to actually say that. We're not going to do any calculations for that. Easy. The calculations in the y dimension cancel out because they are balanced. There's no acceleration in the y here. There's a pull of tension, force of tension, going this way, and there's a force of friction that's resisting it, equal to 150 newtons. This force of tension is coming from this block here. So when we kind of get to this force of tension, we need to think about, well, what's happening down here? Well, here we have 20 kilograms, which causes, if we draw a force diagram for those two masses, 200 newtons of force. That's Fg. And they also have Ft going up. Well, this Ft and this Ft are actually the same Ft because they you can't have two different tensions in the same string. So we have to go ahead and consider that both of these are interacting at the same time. The whole system is going to accelerate in the same way because it's all connected. So we need to think about the net force. The net force is going to be, let's see, let's make our equations here. This is going to help us out. And we're not going to put an x and a y because it's kind of happening in one fluid motion, both in the x and y. So it gets a little confusing because this we would say is in the y, this we would say in the x. We're just going to say the acceleration's all happening in this positive way, which is going this way, and then it's going down as it goes across the pulley. So the forces that are acting in that direction are going to be a positive 200 newtons caused by this pull of the masses, and there's going to be a negative 150 newtons from this resulting friction. So we actually are able to get that net force very easily to a positive 50 newtons. And this ends up being a pretty simple question when we break it down like this. We know that the second equation is just the mass times the acceleration. Again, I'm not going to put an x or y on here because it's in one fluid motion around the pulley. So we can set these equal to each other, that positive 50 newtons is going to equal that mass times the acceleration. Well, the key thing to remember here is this mass. You have to consider the entire mass of the system, total mass of system, because not only is this mass accelerating, this mass is accelerating as well. So when we put that mass in there, that positive 50 is going to equal 50 plus 20, which is going to be 70 kilograms times this unknown acceleration. In order to find that acceleration, we just divide both sides by 70. I'm going to pull up my calculator here to get a decimal. We're going to have 50 divided by 70, and we'll get 0.71. Acceleration equals 0.71 meters per second squared. And since we said this was our positive direction, we'll give that a positive sign. So the key thing to remember here was that this net force, we kind of skipped the middleman of this force of tension. The net force came between this 200 newtons pulling down and this 150 newtons resisting that 200 pulling down. So we were able to create this net force on the system by just using that weight of these two and the friction between the surface and this block. And that gave us a pretty simple 50 newtons of net force. And then it was just using the mass of the entire system of 70 and then solving for that unknown acceleration.